Hi everyone, this is Mr. Bozade, and today I'm going to be talking to you about projectile motion, things that are moving in the X and the Y direction at the same time, things that are flying through the air, like a launcher shooting a ball or a soccer ball getting kicked and it's flying through the air, kicking off the ground, landing back on the ground again. Probably the most important thing that I want to communicate to you here is this statement. Two-dimensional projectiles move simultaneously in the X and Y direction, but the X motion is independent of the Y motion. So let's think a little bit more about that statement. Essentially, let's start with the word simultaneously. We know that simultaneous means two things happen at the same time. So in this case, we're talking about the X and the Y motion. In other words, if we look at an increment of time, like say from here to here, we know that what's going to happen is a projectile is going to move some distance in the X direction during that period of time, like that far. But in that same period of time, it's going to move some distance in the Y direction, like that far. And so that's what we mean by simultaneous. It's moving this far in the X direction and that far in the Y direction as it travels from here to here, and so it's doing those two things simultaneously. So what about this word independent, right? How is the X motion independent of the Y motion? Well, we know independent means that two things don't have to do the same thing. And in this case, the X motion can be different from the Y motion. That's how they're independent. But how is that possible? How is it possible that the X motion could be different or independent of the Y motion? Well, it turns out that forces determine how an object will move. If an object has a net force on it, then it's going to accelerate. If an object has no net force on it, it's going to move at a constant velocity. Now, that's all pretty complicated stuff, and we'll spend a lot of time on that next unit, but I wanted to give you kind of a quick heads up on that. However, the interesting thing is that forces only kind of affect or dictate the motion along the axis that they point. And we know that projectiles only feel the force of gravity on them. And we know that force gravity points down are only in the Y direction. So since it only acts in the Y direction, it's going to influence an object to experience or feel accelerated motion in the Y direction. On the other hand, in the X direction, we ignore air resistance. And since we ignore air resistance, there are no forces in the X direction. So the X direction is going to experience constant velocity. And we can see here that these two motions are independent of each other. They're different from each other. The Y direction experiences accelerated motion, but the X direction experiences constant velocity because of the way that the forces act on the object in the X and the Y direction differently. So that means that in the Y direction, our object's going to follow our accelerated motion model. But in the X direction, our object's going to follow our constant average velocity model. How does this look for a motion map? Well, let's think a little bit about that. We know that if we've got an object like a soccer ball that's kicked from the ground and it lands back on the ground, it'll follow a path like that. We know that the motion map for constant velocity looks like this. It's going to look like points that are evenly timed apart but have the same velocity vector every time. And because they've got the same velocity vector every time, each increment of time they're going to travel an equal distance. And so we see these dots are equally spaced out apart. Well, we find the same thing to be true for our motion map, like this. And what we see as the object flies through the air, in the X direction, the velocity vectors are equal. And because the velocity vectors are equal, because it's going at a constant velocity, we see that it travels an equal distance in the X direction for equal intervals of time. So what about our Y direction? Let's remind ourselves of the motion map model for the Y direction where we've got accelerated motion. Well, the motion map model looks like that. So the object is going up to the apex and it's slowing down. And we can see that it's slowing down because the velocity vector is large to start and it's getting smaller and smaller. And since it's slowing down, it's going to travel less distance each increment of time. The distance gets smaller and smaller each increment of time. And we see that in our actual object as it travels up to the apex. So the velocity vector in the y direction is getting smaller and smaller until it's 0, right? At the apex, the y direction's velocity vector is 0, and it's going to travel less distance each increment of time. On the way down, we see kind of the same thing, right? On the way down, we start with a velocity of 0, and our velocity vector gets bigger and bigger as we travel down because we're accelerating downwards. And as a result, we're going to travel a larger and larger distance every time. And again, we see that to be true for our projectile. The velocity vector in the y direction is 0, then it gets bigger and bigger, and it travels more and more distance each interval of time. So that's how the accelerated and the constant velocity models play out at the same time, simultaneously, in a motion map. So we've got our big idea here about simultaneous x and y motion, but independent. And we know that in the y direction, there's an accelerated motion model. In the x direction, we've got this constant velocity model. So how does this influence the way that we list our variables? Well, let's start with that word independent. If we start with that word, what we see is that when we list our variables, we're going to list them in the x direction and the y direction separate because it's moving in the x and the y direction independently because they're going to be independent of each other. It's moving at both. But we know that it's moving in the x and the y direction at the same time. And the way we currently have it listed is we've got this time down here twice. We've got that listed twice. But that doesn't really make sense because it's moving simultaneously. So what we're going to want to do is erase that and replace it with a single time. That is helping us to see that you can't have a different time to travel a certain distance in the x and a certain distance in the y. It's going to be the same amount of time to travel some distance in the x and some distance in the y. How about this accelerated motion model in the y direction? Well, we know that because gravity is the only force acting on it, its acceleration is going to be the acceleration of gravity, and the acceleration of gravity is 9.8 meters per second per second. We'll make it negative because it points down in a downwards negative direction, but this means that every second the value of the y component of velocity is going to change by a value of negative 9.8. What about the constant velocity model that we're applying to the x direction? In the x direction, that means our acceleration is 0 because we're not speeding up and we're not slowing down. In other words, our velocity in the x direction is changing by a value of 0 every second. It's staying the same the whole time. It doesn't really make sense to have an initial and a final velocity in the x direction because it's constant. So let's erase those and replace them with just one single variable, like constant velocity, which is the same as average velocity because it's constant. And the initial and the final values are the same. So there you have it. That's how all of these important ideas apply to the way that we list our variables. Hopefully this video has helped you kind of lay an important foundation of your understanding of projectile motion and how that motion plays out in the x and the y direction. Thanks for listening. I hope you took some good notes, and I'll see you soon. Bye.